Yeah, thanks for the introduction. So yeah, good afternoon, everyone. So I'm very happy to introduce our research recently. Because in the keynote speak in the afternoon, they mentioned the most case they want to study is like turbulent combustion and the different pressures, like high pressure. That's what exactly we do in this talk. So this is a joint research between STFC and Peking University in China. So yeah, firstly, the background. So like you might see it in throughout this conference, like the hydrogen combustion is quite like popular talk in the recent years. Mainly because of the driven of the carbon neutral target. So like basically the hydrogen will be used like as a energy source for most like mobiles, airplanes, cargo ships, the cars. So but yeah, it's also been mentioned in the keynote speaker, like people are still know very little about the hydrogen flames because it's the burning velocity is so much higher than some like other carbon-based fuels. So like so we need to understand more about this like hydrogen combustion before we can use it in scale. So for this purpose, so like we we study like the how the interaction between the turbulence and the hydrogen flames using direct numerical simulation. And the software we use is called Asta Code. So you might see the one application in this morning talk. So it's supposed to be like a high compressible numerical solver with some multi-physics problems. So it's a high order, like finite difference method on with a structure mesh. So the code was originally designed for study of like shock involved problems like hypersonic applications, shock boundary interaction, also some classical turbulent flows, and being like within recent like 2 or 3 years, it's been deported into combustion. So basically, yeah, so also have very quite satisfactory acceleration issues on the modern distributed memory HPC systems. This is a performance on Archer 2. So it's you see it have linear. It's have a it's have a linear acceleration up to like 200,000 cores. Okay, so basically we couple the obstacles with chemistry laboratory Cantera, so then we can enable the Astra with the simulation with the capability of simulating reacting flows. So basically, it's quite straightforward because there's a Fortran code. The Cantera provide a Fortran interface. So basically, and each time step, the Astra pass the flow variables like pressure, density, velocity, mass fraction to the Cantera, and the Cantera return back some like chemistry related parameters. So such like a effective binary diffusion of species, rate of change of a species due to the chemical reactions. So yeah, basically everything works. So for that case, we're trying to do the experiment being done in the Leeds University. This is the Leeds MK2 Fang vessel. So basically it's like a steel sphere. So like four fans connect to the sphere, use a fan to generate isotropic turbulence. And then there was some ignition in the middle, so they can study like turbulence combustion interaction. So we do the DNS, but we don't have a fan in the DNS, so we use like the body force. So using the random body force, the body force to driven the flow from laminar to turbulence. So this is the turbulence structure. So you see like the turbulence is very close to the isotropic state, similar with the experiment. So this the force is kind of just like two like sine waves. So very simple. So it's inject the energy through the largest scale and let the energy like transfer to the smaller scales. So there's the one parameter control the strength of the force, which is Fr. So Fr is with a bigger Fr, the force become bigger. Fc is equal to 0. So we do a simulation. This is a simulation the isotropic turbulence without any reaction, but we soon see like the turbulence, the velocity fluctuations reach to the statistical steady state. So very soon, very rapidly. So we are happy with the kind of this body force. The force can ensure the flow to turbulence within a very small computational time. I'll do some calibration. This is an experimental measurement. So you see like the the velocity fluctuations in the experiment, the velocity fluctuation increase linearly with the rotating speed of the fan. So with the high speed of the fan, the turbulence becomes stronger. And in our simulation, so we see like also the velocity fluctuations increase linearly with the square root of the FR. So with a bigger FR, the velocity becomes stronger. So we can match them with the experiment. So actually there's some simple fitted formula. So basically the FR should be like linear related to the fan speed. So we see like the two match quite well. So we can do the simulation of any fan rotating speed in our simulation. So this also fit tried the simulation with a different domain size. Basically, actually the velocity fluctuation is linear to the square root of FR multiplied by the domain size. So basically, with two different domain size, the curve fitting quite well. So this is the energy spectrum of the velocity fluctuations, and we see like with a higher velocity fluctuation velocity, which means higher turbulence Reynolds number, and we'll see a longer like inertial range, so which is sensible to us. So we can, at least we know like in this way we can get a like a fully developed close to isotropy turbulence as we expect from experiment. So use that method, we do the simulation with the reacting flow. So this is like the six. But in a simulation, we didn't do like the sphere vessel. We do like a rectangle domain. So we put like the six like isotropic turbulence one after another, and use a force to driven them to turbulence, and we put an initial like a planar flame in the middle. So then also it's a premixed hydrogen gas. So the equation ratio equals to 0.6. So this is a mesh size. And we use like a 6-order compact central scheme with 10th-order compact filter. So very high numerical method. And this is like we see like we're supposed to observe the interaction between turbulence and flame here. So we did a series of studies. One group is under a lower pressure, so like 2 ATM, and the other is the 5 ATM. So they all have the same equilibrium ratio 0.6. But with different like velocity fluctuations, the different levels of turbulence intensity. So we try to understand like how the interaction behave differently with different turbulence intensity and different pressure. So this is the some animation we get. It's moving. Music doesn't matter. So basically, you see the turbulence being generated and the flame being strongly disturbed by the turbulence, and also the flame being progressed upstream, because basically the turbulence accelerates the burning velocity, so they go up much upstream. Yeah, we just show this case for several times, and yeah. Yeah, so we like do some quantitative analysis. So this is like the comparison of flame surface structure after the flow being like reaching to the statistical steady state. So this is like the iso volume of the heating releasing rate. So the upper groups show the result and the 2 ATM. The bottom 4 is the result and like 5 ATM. So this is like from left to right, the velocity, the turbulence intensity increase from U prime 2 to 20. So in case of the same pressure, as the turbulence intensity increase, the wrinkle of the flame surface also increase. You see, like basically the flame front have like presented like smaller structures, and heat releasing rate in a high pressure case is higher than that in a low pressure case, which matches our expectation. And also this is like the 2D section of the simulations and the 2 ATM, and you see how the turbulence interaction with the flame front, basically with like higher velocity fluctuations, the flame was being like disturbed like much more strongly. And you see, for some cases, the high temperature zone is observed much upstream of the flame. So which means like it's because of the the strong turbulence interaction bring some high temperature zone upstream. So also, but this domain is only a part of our computation domain. It's not the entire domain. So this is the result of, yeah. This is the result of the end of 5 ATM. So you see, like if you notice the basically the flame front is thinner. This is also quite match our expectation, and we also see like the local flame extinction. So here, like the local temperature getting lower, and the heat releasing rate is also largely reduced, and this is due to the strong strength of the flame surface. And then we do some analysis of like quantitative. Well, it's not lag. Okay, so we do some quantitative analysis of the PDF probability density function of flame curvature. So the horizontal axis is the curvature, and the vertical is the PDF. So so like in case with the same pressure, the peak of the PDF is lower and shift as the turbulence intensity increase. So basically, which means with stronger turbulence, you get like more curvatures, like which means as we see, like the flame front become more wrinkly. And moreover, in case with high pressure, so basically all the curves are becoming flat. So the overall peak of a PDF will shift further to the positive part of the axis. So the local flame dispersion speed is augmented. So the results are consistent with the phenomena we previously demonstrated of richer flame curvature in case with high pressure and higher turbulence intensity. So then we do some try to model a bit of the turbulent burning velocity with different pressure and different turbulence intensity. So this is how the turbulent burning velocity is calculated, and we focus on the ratio between the ST, which is the turbulent burning velocity, to the laminar flame speed. So basically, for all the cases, you see after a certain time of this simulation, all the results reach to the statistically steady state. So then we do some average, and we get some like the statistical mean turbulent burning velocity, and we can compare with the model proposed by Lu and Jiang in 2020. So basically, in his model, the turbulent burning velocity is basically related to the turbulent flame area. So this is how the turbulent flame area is calculated, and then this like the ratio between the turbulent burning velocity with the laminar flame speed is a ratio to the I0. I0 is the strength factor using a table for the laminar flame data. So then basically the velocity, the turbulent flame area is related to the turbulent intensity here. So then they have this ST model like this, and we compare our result to their models, basically with the increase of the velocity fluctuations. So the turbulent burning velocity increase and then become flat. So for the higher pressure, basically the turbulent burning velocity will a little bit higher, but it eventually also be flat. So but the most importantly, we observe some quite a good agreement of our DNS data and the models on the different turbulent intensity and the different pressure. So basically, this is still a very preliminary study. So basically, we developed a deterministic force method to maintain statistically stationary isotropic turbulence for studying our flame turbulence interaction. Basically, we try to numerically mimic the MK2 vessel of the Lee's vessel experiment. So and we get a linear relation between the force and the turbulence intensity, so can match up the experimental facility. And by using this kind of forcing method and high order solve ASTA, we studied the hydrogen flame turbulence interaction and the different turbulence intensity and the pressure. And we reached some preliminary scientific observations. So we see like the disturbance of a flame front by the interaction with the turbulence, and higher turbulence intensity leads to more complicated flame geometry and higher turbulence burning velocity. The increase of pressure also enhances chemistry reaction, leading to higher heat releasing ratio and temperature around the flame front. So also the curvature of the flame front and the turbulence burning velocity are also enhanced by the increase of pressure. So the bending curvature of a turbulence burning velocity are observed, and the result agree well with the model proposed by Lu and Jiang. So, and we're still working to try to in-depth analysis. And we also recently improved the forcing method, make it more isotropic. And so, yeah, the simulation was all done on Archer 2, and the computation time is awarded by the UK Deterministic Consortium. So this collaboration is supported by the Royal Society International Exchange Scheme. And thank you very much.